Hello. I would like to introduce Gabriel Parmer, Associate Professor at George Washington University, who does all sorts of cool work with the Linux kernel and research operating systems. And recently he's been toying around with scalable updates utilizing modern features in x86, such as invariant TSC. Gabe is a very humble man. He asked me not to do an intro, but anyways.
So he did the longest intro. Yeah. I just need to learn. Tell Sammy the thing that I don't want. So I am the person who is between you and drinks, food, socialization, and sleep, which is not a good position to be in. So we'll see how this goes. So I'm going to be talking about some of our more recent work on an RCU type thing. And this work was really built on the back of a lot of work from multiple people, including a lot of grad students, one of who's in the room, Jigwo. So I don't want to say that this is my work entirely, but I was one of the many people who collaborated on it. And we're at George Washington University in DC. So I think everybody's seen this graph. This is probably old hat to pretty much everyone. You have dates on the bottom going up to now. You have kind of magnitudes on the left, on the y-axis, and you see the red line, Moore's law, right? So we get more transistors over time, and the y-axis is exponential, or is logarithmic, sorry. So the straight line means exponential increase. Great, we like transistors. What you do see is that at around 2006, some of the other lines started leveling off. Dennard scaling stopped. We started saying, okay, we've been able to shrink transistors, and we didn't have to pay an increased amount of energy or power for putting more of them onto the board. But then leakage happened, and we couldn't do that anymore. So you see megahertz kind of trailing off. You see a few of the other things trailing off. But what you see is, of course, we have the transistors. We need to put them somewhere, so the cores increased. So I want to point out here that single-threaded performance still is increasing, but is increasing at a lower slope. If you look at the high slope, that was what was called the free lunch. That was what was called you write your application, and it can suck, because in 2 years, it won't suck anymore, right? But we don't really have that anymore. We have this much lower slope, and we need to deal with it in some way. So like I said, we're dealing with it by having an increasing number of cores that we need to learn how to deal with. Many people in the room know how to do that very well. But the world at large does not. So pre-2006, it was fine to do things like this. When we enter into a system call in an operating system, had something like a big kernel lock. Because when you don't have multiple cores, nobody cares. And you might as well have core screen locking because it's a simple thing to do. Afterwards, that's not so acceptable. Now you have a lot of contention on that lock. And in the end, Amdahl's law is going to limit what you can do. So you might see that we're kind of leveling off a little bit in the number of cores. We might be, we might not. So we have Knight's Landing processors that Intel has given us, and they have 72 real cores on them, 144 hardware threads, right? Hyperthreads. And those are not coprocessors anymore. Those are actually the real processors on our system. So that's a lot of cores that we have to deal with. We have HP Superdome systems that don't just have a lot of cores, but they also have a lot of sockets. So now, of course, we need to worry about locality in our parallelism. So these are things that we really do need to care about. I don't think I need to convince anybody in the room, but okay. So how have we dealt with this? How have we said we need parallelism, we need to use it, what do we do? Many techniques. We have done the obvious one, partitioning. Web services are based on the idea that we can have multiple memcached servers, multiple web servers, and they can act independently, share nothing. We use fine-grained locks. We architect our data structures so that we take locks for smaller portions, hold them for smaller amounts of time. We use non-blocking algorithms, my favorite of which are included in a wonderful library that you should check out called Concurrency Kit. Sammy is one of my former students, and I still use his code on a daily basis. And we use synchronization-free read paths. This is made most famous with RCU and friends. And that's what I'm going to be talking a lot about. So to motivate some of this, I want to use an example. And we have a data structure on the bottom with a number of nodes, and it's something like a hierarchical file system. We have node A that has B, C, and D as children within it, and node C has E and F within it. I'm very sorry, normally I can look at the screen to discern this, but okay, now I'm craning my neck. And we have a core that wants to walk through ACE, right? So you can see it's going to take a path through the data structure, no problem. We have another core that wants to do a walk through the data structure for AD. It walks through the data structure correspondingly. We have to answer the question when we are writing these things, how we synchronize the two, how we maintain consistency while still getting the highest performance. The problem is that many naive schemes are going to require us to be writing to the cache lines of these nodes as we go through them, using things like reference counts, taking things like locks, and it's going to cause a lot of cache line bouncing between the caches of these cores. We'd like to not do that. So the easy way to do concurrency is to just use basically big kernel locks, but one per data structure, coarse grain locking. This is great in that it's simple. I love simple systems. Some things are simple to a fault. This is simple to a fault. Amdahl's law limits us here, right? We know that we have a sequential section now while accessing the data structure, and the length of that sequential section limits the parallel speed up that we can have from the system. So not so good. So we move to fine-grained locks. Okay, cool. I take a lock on A, and then I go look through its siblings. And then I take a lock on C and release the lock on A. So now I'm taking these locks for a smaller amount of time. Amdahl's law still limits us, to be clear, but not as much. So that's good. We have progress on that front. But now again, we're modifying these cache lines as we walk through the data structure. So when we're even just doing loads from any of these nodes, we're pulling cache lines into our cache where they might have been invalidated before. This is all overhead that doesn't scale very well as we add more and more cores onto our system. So the goal then is that we want to avoid all this. We want to avoid, at least in the read path, cache line modifications, right? And in the update path as much as possible. So the first part of this talk, I'm just going to be talking about one technique that is inspired by a lot of the work before, like eBlock-based memory reclamation and RCU, that tries to do this in one way. So there are many things that can go wrong when you say, oh, don't write to cache lines. It's no problem. The most obvious problem is things like consistency. If you aren't writing to the cache lines as you walk through, how are you synchronizing with other people, right? The less obvious problem, if you aren't familiar with RCU and the like, has to do with liveness. And here we have 3 pieces of code, each being run by 3 separate cores. In the top left, we're walking through the data structure and we're processing on the node that we find. In the middle, we're walking through the data structure and deallocating the node. And in the bottom, we're just allocating a new node and initializing it, right? So the last one seems particularly innocuous. Now, of course, because these are run in parallel, we can kind of order them and look at adversarial interleaving. That adversarial interleaving looks something like this, where we walk through the data structure, find the node that we're interested in, and then we go and deallocate that exact same node, allocate new memory, and we might happen to allocate the same memory that was used for the recently deallocated node. We initialize it, putting it into an initial state, and then, oh crap, we go back to the first core that is going to process on this thing that it thinks is at the applicative 16 place in the data structure, but no, it's freshly initialized. So this is a fundamental problem when you aren't doing synchronization. And Paul already went over a lot of this in the previous talk yesterday, so this is a different perspective on how to think about it. So what this points out is that we really just cannot reuse memory until there are no more references to it. When you hear the word references, you should think, okay, well, we have techniques to deal with that, use reference counts and the like. Using reference counts goes back to modifying the cache lines within the data structure. We don't want to do that, right? So the goal is to try to discern liveness of nodes, or whether they're referenced or not, without, around this data structure, without touching shared cache lines where possible. So there are many techniques for doing this type of thing. Like I said, epoch-based memory reclamation, RCU, whatnot. And I'm just putting all of these into a single term, which is scalable memory reclamation. I didn't choose safe memory reclamation because that's really what epoch counters were initially named. So bear with me with this kind of bundling term. The API for some of these things, or an API for some of these things, is that you annotate when you are accessing a data structure, just like you would with a lock, except you aren't locking anymore. You're just saying, I'm going to enter into my references for the data structure. You walk through it, you do your processing, and then you say when you exit. The important thing is after you say that you exit, you're no longer referencing any of the nodes. This is kind of an implicit contract with the API, right? Just like with locking. When we update the data structure, we enter just the same. We go through and do whatever we need to do. We exit, and then we want to do the synchronization operation, where we say, okay, I need to wait until no other parallel core could be accessing the data structure before I actually go through and deallocate this thing. This is one of the many APIs. This is just the one that I'm going to be borrowing for this talk. Graphical way to depict this is that we have two cores, one on top, one on bottom, time going from left to right, and each of the boxes denotes one of the enter-exit pairs, right? So we enter, the box start, access the data structure, exit, box ends. So we see here that core 1, yes, enters and exits, fine. Core 0 at some point deallocates node S within the data structure. And if we try to do reallocate that same node at the second time where the allocate is denoted, we have a problem. We have exactly the problem that I was talking about because core 1 can still be accessing that data structure, right? So what we want to do is say, no, you have to wait till later till you can actually reclaim that memory. And the question is, how long do you wait? And I'm not talking in terms of time. I'm talking, when semantically is it okay to wait till. And we determine a grace period here. So the grace period is when we actually can reclaim the thing. And we ascertain quiescence, which is when we can actually go through reclaim the thing. And that's the question that we're trying to answer. So we have a technique called Parsec, parallel sections, that does this same thing. I'm going to talk about it with respect to RCU. And the question is, how do you do this computation for grace periods for quiescence in a way that is scalable? So this is really kind of the core contribution that we're trying to make here, this notion that you can compute this update path scalably. Okay, now before I go into that, I want to depict how you could implement this in a way that won't be scalable, just to give you an impression of what we're talking about here. And this is code that's very, very, very loosely based on URCU, user-level RCU. I'm interested in preemptible systems because I care about latencies for things like interrupts. So I am only considering preemptible techniques here. So this is a vastly simplified URCU type algorithm. When we enter, we essentially set a bit within some thread local state. When we exit, we unset that bit. But we also want to have some notion of time, when we're actually within this critical section. So we have a counter, say, that just counts the number of times that things have been freed and saves that in the same word when we enter. So now when we're in a parallel section, we're saying, I'm in here, please note that. I could be accessing the data structure. And I'm accessing it when this number of pieces of memory had been freed. When we synchronize, num3++, and then we spin, we wait, we perform this synchronization operation while there exists some core that can be accessing the data structure, so access is set to 1, and it's accessing the data structure at a time when it could be accessing the nodes that we're checking on. So why is this not scalable? This is not scalable because, well, I'm going to denote that here. In the top right, this is very confusing with the mirrors in back. In the top right, you have the code that I just picked, and I'm going to be highlighting the pieces of the code that are kind of being acted on in the diagram. In the bottom left, you have the diagram of actually cache lines bouncing around in the system. So we have the num_freed global variable in the center that's red. It's red because that's probably a contended path, or a contended variable, sorry. And we have the same boxes. Okay, so when core 1 enters into one of its data structures, it reads in or loads this num_free variable. It might already be in the cache, especially if it hasn't been, if there hasn't been an update in a long time. If it's not in the cache, it pulls it in. When we do sync, we store to num_free. Storing to num_free is probably going to invalidate all of the other num_frees and all of the other caches throughout the system. And we're going to iterate through all of the thread local data structures for the other threads on the system, which is going to take all of those wonderful cache lines that were local in their cache and move them over here, probably into a shared state, whatever. So that has n overhead. There are n cache lines bouncing around. And then when we go and we try to just enter into the critical section again, we need to reestablish our state, which moves cache lines around some more. You'll notice this is one sync operation that has around O of n cache lines bouncing back and forth. If you have n operations that are syncing, now you start having n squared overheads. When you start seeing these n squared overheads for messages being passed around in distributed systems, that's when you start realizing that things are probably not going to scale very well. Now, of course, this is a straw man example. I mean, there's nothing that is this stupid. So I'm really using this not as an exemplar of some technique, but more as an exemplar of how you could do these things badly. So that said, URCU does have approximately this much cache line traffic. It optimizes away a few cases. So those types of techniques are mainly used for read mostly data structures. As Paul said in his slides. Yeah, please.
You got an old version of URCU recached now. So what happens if a whole bunch of people simultaneously want to wait, they do one operation and piggyback off that one? Say that again, Steve.
So they help each other, right? That's what you mean? Yeah. So if you have, no, I don't have an old version. This is a simplified version. I'm not going to be able to put that on the slide. It's really, actually, the implementation is really cool. You have a situation where when you are trying to do this quiescence operation and somebody else is, you actually say, okay, let's not all do this. So you avoid that n squared types of overhead. Instead, one waits for the other to complete it, which is a really cool optimization. So we want to get away from O of n. So this talk is about using time. How can we use time in an intelligent way? A lot of the work that I do is in real-time systems and operating systems. So I had to insert that in some way into parallelism. So we want to use time here and implement our version of parallel sections, Parsec, with that. So how do we do that? There are two main observations that we make. The first is that we have invariant TSCs on modern Intel processors. Invariant TSCs simply state that you can take a timestamp on one core, and that timestamp compared to a timestamp on another core, they're directly relatable. You can basically apply less len on them and determine which event happened before the other event, modulo some uncertainty. So that's really cool, and this works independent of frequency scaling, all of that stuff. Even sleeping. A node can go to sleep, and when it wakes up, the timestamp counter it reads will be consistent with the rest, right? Which is really cool. So we observe that there is this hardware support on modern Intel processors, and we observe that this gives us a local way to get at time without reading any global cache lines. So that's really nice. The second observation, this is probably the more interesting one, is that we can actually compute quiescence not for the current time, but for a time sometime in the past. So we don't need to say, right now, I want to make sure that I can achieve some form of quiescence. We can say, oh, you know what? I actually freed this memory 2 seconds into the past. I should check to see if this system is quiescent 2 seconds ago, not right now. And that's a really powerful thing. Additionally, I'll get to optimizations later. So a few of the nice benefits of this is that the implementation is weight-free and that it never blocks, yet it guarantees that memory can be reclaimed. If you aren't deep in the trenches on these types of implementations, that probably doesn't mean that much, but it's an interesting invariant. So how do we implement this? Again, this is a simplified kind of straw man example. The code is online. I'd be happy to point anyone to it. You can find a pointer to it from my webpage. When we're entering and exiting, all that we're doing is taking timestamp counters, saving them in local data. When we're freeing, we're tagging a piece of freed memory with the timestamp counter for when it was freed. That allows us to compare when memory was freed with the current time that different threads are executing in their parallel sections. And we can use this to ascertain a global ordering between these events. So in Parsec, what we're trying to do is say the memory can be referenced and therefore we cannot reuse it, we cannot reclaim it now, if there exists some thread where enter is less than freed, so it entered into its parallel section, and after that the memory was freed. And second, if, and honestly, like I wrote this code and I always say this incorrectly, so I just want to read it, where tenter is greater than texit. So if tenter is greater than texit, then we have a situation where we're in the parallel section. If exit is greater than enter, that means we entered and then exited and we are no longer in there. So, what's that? What if TSCs are not invariant? So then you have to emulate your global version of time using software.
No, I think this could also be true if something goes wrong with the TSCs.
Okay, if something goes wrong with the TSC, yeah, I mean, if something goes wrong with your hardware in general, you're in a pretty bad spot. So what we do is, I mean, actually they publish in the spec, so in the Intel architecture manuals, they say you can have some drift. I mean, any type of distributed time system, you have to accommodate some drift. And what they say in the architecture manuals is that 2 TSCs for 2 cores might drift out of sync over time. And the amount that they drift out of sync is something ridiculous, like 2 nanoseconds a day. If that became an issue, which it very well could, especially in long-running systems, you have the facilities for being able to reset them dynamically. The kernel can do that. So that's important. Okay, so I just want to do a very simple kind of semantic comparison for how this technique compares different to epoch-based memory reclamation, et cetera, some of the other techniques from before. So here we have a comparable graph. We're entering, we're exiting, we free in core 0, and when we try to reallocate that memory, or when we try to reclaim it in some way, yet it could still be accessed by core 1. In Parsec, we say, no, you just can't use that yet. And you go and allocate new memory instead, okay? In a lot of the variants like epochs, RCU, if you aren't using some of the other APIs, you spin and wait, right? And if you aren't doing that frequently enough, I mean, if you aren't doing that too frequently, it probably doesn't matter, right? But in this case, it would. Later, when you try to allocate, so let's assume that you didn't allocate there. Later, if you tried to allocate after core 1 gives up all of its references, you have a situation where Parsec can say, I want to see if I was quiescent back when it was freed. And we can see that cores 1 gave up its reference between the time when the memory was freed and now. So it's no longer possibly reachable. So we're ascertaining quiescence for a time in the past when the memory was freed, not for now. Most of these other techniques say, all right, I actually want to ascertain whether I'm quiescent now, and that means possibly spinning at that point. There are variants in this. Maybe you don't spin, maybe you just do a poll-based approach, but then it's hard to guarantee that you can actually reclaim all of memory. Paul.
There's a
So that's an option, but then guaranteed memory reclamation becomes hard. Progress in memory reclamation. So there are a number of optimizations. So if you paid attention here, you'll actually realize that I've kind of waved my hands around a lot, but I haven't actually made much progress because I said we ascertain quiescence by seeing if there exists one of the other threads, let yada, yada, yada. If there exists one of the other threads means going through all of the local data structures for all of the other threads. So we actually haven't bought much in terms of the efficiency of update. But there are a number of optimizations that make it possible to minimize the amount of state that we need to actually read in from remote caches when we're quiescing. The first one, and the really big one, is that once we figure out a quiescence value, we can cache that. So we cache that value and reuse it again and again as we try to reclaim memory. More importantly, because we're saving that somewhere, when I'm walking through the other threads structures, I can look at their quiescence value. Because I have a global ordering of all of these times, a time that they computed for quiescence is valid for me for quiescence. So in the common case, I actually don't walk through all of the other thread structures. I walk through one until I see that it has done the hard work before and computed quiescence for me. There are a number of other optimizations that we do, and I'm going to refer you to a paper because they're far too complicated to explain here. So if we look at a micro benchmark that is dangerous enough because it's too small, we have along the x-axis the number of cores, along the y-axis millions of operations per second. We are doing 10% updates, which means 10% is kind of freeings and all of that stuff, 10% syncs, and therefore 90% reads. And if we look at the scalability of the system for the read path, which is the left graph, we have red, which is Parsec. We have green, which is URCU. We have blue, which is epoch-based SMR, and we have yellow, which is big reader locks, right? A scalable read-write lock. So if we look at the scalability of the read path, RCU and Parsec do relatively well. They are both scalable. Parsec is at a higher slope, so it uses the increased cores better in this case. And that really just comes down to the fact that it's not reading that global variable that is bouncing around every single time that we do the sync. We have local access to global ordering, so we don't access anything global there. For the update path, Parsec actually scales linearly as well. It's hard to see because this is a log scale. And the rest of the techniques that aren't really designed for this type of a case in general, they do not. They don't use the parallelism well here. They aren't designed to, so it's not necessarily surprising. So that's fine. We wanted to wrap a couple of abstractions around this. So just because you can walk through a data structure without modifying any cache lines doesn't mean that you've now magically solved all of the problems, right? You still need to update your data structure and you still need to have some consistency guarantees. So we introduce these Parsec locks, which are just a very small modification on traditional locks, and they allow us to walk through a data structure using the SMR, allowing us to not modify any cache lines until we reach the node that we're interested in. Then we lock just that node, do our operations, whether we're locking for readers, whether we're locking for updaters is up to the consistency guarantees that you need. But we go on, perform our operations, and then unlock it. So these sound like normal locks. They're just two slight modifications. And these two slight modifications are important to understand. One is that when we're taking a lock, we can have a really, really awkward race condition. Somebody, because we're all walking through this data structure at the same time, somebody could have walked through the data structure and freed the node, yet we still have the reference to the node, and we're going to lock it. So we could lock a freed node. Not a good idea. So the lock take, actually returns a value. It returns success or failure. It looks more like a try-lock type primitive because we could have the situation where we tried to take a lock and it fails because the node has already been freed. Comparably, we have this call for releasing, where we don't just release the lock, but we also free it. Both of those things as kind of a atomic operation. So, small modification to locks. Now, the downside to just using these locks along with SMR is that now we are modifying a cache line. Luckily, it's probably only the cache line or cache lines of the node that we are really updating, so that's good. I mean, you can't really get away from doing that. But as we walk through the data structure, we're moving all of the cache lines that might have been modified because of other people taking locks in those nodes. We're moving them over into our cache. So as we walk through the data structure, we're incurring a lot of cache movement naturally. So we want to do a little bit better than that. So again, this is a very, very slight modification on what people have been doing for a very long time, but it fits into a cohesive abstraction. We provide namespaces, which are a lookup between a descriptor and specific nodes within the data structure. So you really want to short circuit the data structure. You want your walks to go directly from you saying that you want to look up a node directly to finding that node. So this namespace, as we call them, is really just a mapping between a descriptor associated with a node and the node itself. And it's a wait-free data structure that handles allocation and deallocation of descriptors for us. So this allows us to avoid the problem just using locks. Just want to see how much time I have. I'm actually going to skip this. So this is a result that looks impressive, but actually should not really be surprising to anyone. We took memcached and we ran it with an increasing number of cores. The black line at the bottom is memcached as you try to increase it up to 40 cores. Memcached is not really designed to go over 4 cores. So it's not surprising that if you don't design something for doing something, it's not going to do very well. But we took another paper that was at NSDI, and they said, but you can make memcached much better. This is how. So first, you don't do real LRU, and you avoid taking a lock for the LRU list on every read. That's just going to kill you if you have to take a lock every time you do a read. So instead, they use clock. Clock is pseudo LRU, and it just requires that you write to the actual node itself when you access it. So, okay, that's great. Second, you should actually use locks that don't suck. So the naive spin locks in memcache are naive, in my opinion. Maybe they've been improved since, I hope so. So we took out our trusty concurrency kit and said, all right, MCS locks, use those to protect each of the buckets, right? So MCS locks are great, they're scalable. So the modified memcached line, the green line, is what happens when you apply those types of optimizations, and you get significantly better. But of course, if your read path is not touching any locks, is not really touching any cache lines except for maybe clock, you can do much better. So like I said before, this is not impressive result. It's an expected result. What you do see is the difference between the red and the blue lines is whether we use a cache replacement policy or not. So whether we use clock or not. And that's really interesting because the difference between these two lines, which is pretty sizable, is just whether you are writing to the single cache line of the node that you're interested in when you're doing a read. So just writing a single bit ends up causing that huge performance disparity. Okay, so that's our first use of time in systems. We've used time before, and even though this is kind of the reverse order of the order in which we did the research, this is second in this talk simply because it's a more aggressive use of time and should actually probably make people feel pretty uncomfortable, but I would be happy to defend even my being uncomfortable about it. So we do operating systems research at GW, and we have our own operating system, and the kernel of that operating system is called Speck. I chose Speck because it's very small. It's supposed to be like a speck of dust. And then I go to Germany, give a talk, and they're like, yeah, Speck means like the fat in bacon. Like, all right, tried to choose something that denotes something small and ended up being the fat, right? All right, well, you can't win them all. That's fine. I should actually just stop naming systems is probably the actual thing to draw from that. Okay, so the question is, can all operations for a very minimal type of system be made scalable? This is, I mean, so vacuous almost to be, false completely. So it requires that you kind of say, under what conditions can they be made scalable? So let's go into that a little bit. So the mental model of the system that you should have is that it's a system that all of the kernel data structures are descriptor tables. And really, you can think of these as like file descriptor tables. Every single kernel resource is associated with one of those descriptors. Kernel resources include things like threads, communication endpoints, et cetera, pages, frames of memory, whatnot. So we have these descriptor tables. They index all these kernel resources. We actually call these descriptor tables resource tables, and there are two types. Capability tables that kind of give us access to kernel data structures that are constructed in software, and page tables. Everybody knows what page tables are. Page tables are just a special case of our resource tables. All of the invariants that I'm going to be talking about apply to our modifications to the page tables as well. To be clear, this is a strange system. This is a system that is scalable but has no locks. This is a system that doesn't have a scheduler in the kernel. It implements schedulers at user level. Protection domain boundaries can be raised or broken down on the fly efficiently. It's weird. So there are very few broader lessons that can probably be learned from this. It's more of a case study in how you might implement something like this. So when I say that we have resource tables, what does that look like? So we have components in the system. These are like processes, right? Every process has two resource tables, capability table, page table, which you see here. And if I want to access a kernel resource denoted on the left bottom there, I basically here say, okay, at index X, there is a slot in my capability table, and I can use that to access a kernel resource. So there's actually only one system call in the system, and that system call is perform an operation on that resource at that location. Page tables are the same. We index Y into them in a natural way, and we can modify mappings, virtual memory mappings, and actually kernel memory as well in this case. So, and I promise I'm going to be getting to time soon. So if we want to access a resource, one thing that's really important here is I'm denoting this cache line thing here. So every slot within a capability table is going to fall on the cache line. It's really important. These access to these kernel data structures don't include locks. Instead, they happen just like we were talking about before with Parsec, with only loads. So when I have two cores accessing two slots for two resources on the same cache line, that's fine. That's scalable because it's just loads. There are no locks taken. There are no shared cache lines modified. However, if I try to store, okay, now I have problems. So what the system allows you to do is it makes a very explicit mapping of different indices within resource tables to the cache lines that are backing those descriptors, those indices. So now system software can very intentionally use this explicit mapping between the namespaces that we're using to name all of our resources to the cache lines that actually implement them to, for instance, there are many policies that we use. The simplest is striping. So now different cores are only allowed to store to different regions within those resource tables. So this allows us to completely avoid store contention within the kernel, which is quite nice. Consistency, so we designed the system entirely for this idea. So consistency is brought not with locks, but just by using raw atomic instructions. So we have the same problem that we had before. We don't have locks. We have some things that are freeing and allocating these different resources in specific slots. And we can have a case where one core is accessing a resource while another core is deallocating it. So we have exactly this problem again that we had before. But now we want to more aggressively use time. I don't want to use time by keeping thread local information and whatnot. Instead, I want to use a very specific peculiarity of how we design this specific system. It might be applicable to some other systems out there. We've seen this. The question that we want to answer is, what is the minimum latency for the grace period? So in the previous case, we kind of did this quiescence operation to discern it and whatnot. In this case, we can say the kernel that we've implemented is about 7,000 lines of code. It has no loops that are not statically bounded. It has no recursion, and it's relatively simple. Sum total of all that meaning that the worst case execution time through the kernel is fairly consistent. So I can actually say, well, what can the grace period be? I want to look at the maximum of any of these system calls and use that as the grace period. So the grace period is actually the worst case execution time of the kernel itself. So now when I deallocate a resource at a slot and I want to reuse that slot, all that I need to do is compare whether it was deallocated, at least that worst case execution time, into the past. So we're more aggressively using time here, right?
So how about you handle I/O?
I/O is at user level. We punt.
Okay.
I/O is within the preemptive realm. I/O is where you actually start needing to use Parsec. The reason that we did Parsec is because this cannot be used everywhere. So time for the win. We compare it against another minimal microkernel. The orange and red lines along the bottom show that as we increase the number of cores, operations on page tables for mapping and unmapping memory remain fairly consistent. The one on the right where we're unmapping memory should raise some eyebrows because it looks like it has to be completely false. There's this little thing called TLB shoot down that you typically need to do when you're unmapping memory. We wrap TLB shoot down into a larger grace period and do it periodically to avoid having to do that. So we get consistent unmap as well as map. We combine Parsec for user level, writing a virtual memory manager that exports mmap type functionality on top of the kernel and hit it with a heavy workload of maps and unmaps and compare it against Linux and see that the cost is not consistently low. And the reason for that is very esoteric around using 32-bit systems instead of 64 for these results. But importantly for Linux, it's significantly less scalable, right? Interestingly enough, for Linux, unmap is less expensive than map here, which is really cool because the Linux kernel guys did some brilliant things with deciding actually when they have to do TLB shootdowns. But it's not as effective in this case as our system. So, the title of this talk is Updates Require Time. I hope I didn't convince you of anything because after a talk, you should not be convinced of anything. The code for all of this is up online. What I want to give you the impression of is that using time as a notion for synchronization in your system can be a powerful thing if used properly. And I think that's probably all I want to say, except for a take on Paul's old article, which is that real time is not real fast, but real time is real scalable. If anybody knows that article, like 2 people in the audience probably got that. So, all right, I'm pretty out of time, and I don't want to keep you here, but if you have any questions or comments, please feel free.
Yo. So, yeah, just to clarify though, on the read side, our RCU for read mostly workloads still crushes this because on the read side here we still have a memory barrier that we have to pay, and I don't think it was very clear elaborate on that a little bit.
So for epoch, you mean?
No, for RDTSC.
So for the RDTSC, okay, so you're talking about for read 100% path, right?
Yep. And also, did URCU really beat epoch?
For the read, not for the update. So I actually don't have the result here, I'm sorry. For the read-only path, yeah, URCU is pretty much the king there. Not by too much, but it can very intelligently elide some of the memory barriers, and we've put no effort into trying to do that. We're looking at some of the ASPLOS papers recently for bounded TSO to look into doing that, but RCU on the read-only path is still going to be faster, if for no other reason than because we have to do our RDTSC, which is 30 cycles worth of latency versus local memory accesses. So RCU, if you really have read-only or read absolutely mostly type things, yeah, you should probably still stick with that.
One thing on the, if you can get certain information from your CPU vendors, which is usually not available, but if you're doing real-time and embedded, you might be using some CPUs where it is available. If you have a worst-case instruction reordering and delay, you can skip the reset memory barrier and add that delta to your wait time.
Indeed.
It could be pretty impressive if you did that.
So, I mean, I'm terrified of relying too much on these kind of architectural timings and everything.
You should be.
Yeah. I mean, don't get me wrong, I'm in research. I love pushing the boundary, but pushing the boundary should not involve shooting yourself in the head, right? So what we are looking at is if we can periodically just issue memory barriers, then the periodicity of those memory barriers can be taken into account in the comparisons between the TSCs, which is nice. Then you get rid of the memory barrier. And like I said, I'm between you and drink, food, sleep, socialization, so please, stop talking, stop listening to me. And I think Sammy probably has something to say to close down the thing.
Yeah.
I don't know if anybody else is going to do it, so I would like to thank Sammy and anybody else who was involved in the organization of this entire thing.
Yeah, thanks to the ACM. They really put a lot of effort into this, as well as the practitioners board. Thank you all for attending. Thank you to our sponsors. If we could actually pull up the other deck. Yep, so thank you to AppNexus, Google, and the K Family Foundation, as well as Facebook for their sponsorship of the event. And please tweet, use social media, and all these things that I don't really care about. Yeah. Cool. All right. Well, thank you all.